Have you ever wondered what heat truly is? It's not just a feeling, it's a form of energy residing within all matter. We call this internal energy, and it's the sum of two components. The first is the kinetic energy of molecules, those tiny particles constantly vibrating and moving around. Imagine a microscopic dance floor where molecules are always jiggling and bouncing off each other. The second component of internal energy is potential energy, arising from the forces between molecules. Picture these molecules as being connected by tiny springs. The closer they are, the stronger the force pulling them together, and thus, the higher their potential energy. The interplay between these two forms of energy, kinetic and potential, determines a material's internal energy. When we heat something up, we're essentially giving its molecules more energy to move around and push against their neighbors. Conversely, cooling something down slows down the molecular dance and reduces their potential for interaction. Understanding internal energy is crucial for comprehending how heat flows and materials change. It forms the foundation for explaining phenomena like temperature changes, phase transitions, and the very nature of heat transfer itself. In the sections that follow, we'll delve deeper into these fascinating concepts, revealing the intricate workings of heat and its profound impact on our universe. We experience heat as a flow of energy, always moving from hotter objects to colder ones. But what drives this flow? The answer lies in temperature, a measure of the average kinetic energy of molecules within a substance. Imagine two objects at different temperatures coming into contact. The hotter object, with its more energetic molecules, will collide with the colder object, transferring some of its kinetic energy. Think of it as a game of molecular billiards, where faster-moving balls transfer their energy upon impact. This transfer of energy continues until both objects reach thermal equilibrium, a state where their temperatures are equal, and the net heat flow ceases. It's like the two objects reaching a compromise, settling into a state of balanced energy. Temperature difference is the driving force behind all forms of heat transfer, conduction, convection, and radiation. Whether it's the warmth of sunlight on our skin, the heat from a stovetop burner, or the chill of a winter breeze, it all boils down to energy flowing from regions of higher temperature to regions of lower temperature. Understanding this fundamental principle helps us grasp how heat shapes our world, from weather patterns and ocean currents to the operation of engines and power plants. In the following sections, we'll explore the specific mechanisms of heat transfer, uncovering the diverse ways energy travels from one place to another. We encounter different states of matter every day: the solidity of ice, the fluidity of water, and the ethereal nature of steam. These phases of matter are directly linked to the internal energy of a substance. As we add or remove heat, materials can undergo fascinating transformations, shifting between solid, liquid, and gaseous forms. Consider ice melting into water. At the melting point, 0 degrees Celsius or 32 degrees Fahrenheit, heat energy is absorbed, not to increase the temperature, but to break the rigid bonds holding water molecules in a crystalline structure. This energy, known as the latent heat of fusion, allows molecules to move more freely, transitioning from the solid to the liquid phase. Similarly, during boiling, water absorbs the latent heat of vaporization at its boiling point, 100 degrees Celsius, or 212 degrees Fahrenheit. This energy enables water molecules to overcome their intermolecular attractions completely, escaping into the air as water vapor. These phase changes demonstrate that heat transfer doesn't always result in a temperature change. Instead, it can cause a rearrangement of molecules, altering the very nature of a substance. Understanding these transformations is crucial in various fields, including meteorology, materials science, and even cooking. To understand and predict how heat affects our world, we need to quantify the amount of energy transferred. Two essential equations help us achieve this: Q equals mcdelta T and Q equals ml. The first equation, Q equals mcdelta T, calculates the heat, Q, required to change the temperature of a substance. Here, m represents the mass of the substance, C is its specific heat capacity, the amount of heat needed to raise the temperature of 1 gram by 1 degree Celsius, and delta T represents the temperature change. The second equation, Q equals ml, comes into play during phase changes. Q still represents heat, m is mass, and L represents the specific latent heat, which depends on the type of phase change, fusion for melting or freezing, or vaporization for boiling or condensation. These equations are powerful tools for engineers, scientists, and anyone working with heat transfer. They allow us to calculate the energy needed to heat water for a bath, determine the cooling capacity of an air conditioner, and even predict the energy released by a volcanic eruption. By quantifying heat transfer, we gain a deeper understanding of the energy dynamics at play in our world and can harness this knowledge for countless applications.